Now, we're just after the last pause of today. We are jet lagged and tired, and I already had some person asking me whether he should go and take a power nap rather to listen to me. I didn't give a clear answer to that one. Now,
that was me, by the way.
I'll try to run it through relatively fast, because basically there is no real changes, neither in what we're trying to do nor in the way we are trying to do it. So I'm the team leader, we are small, we have very, very limited sponsorships and very limited money income. What we have is that we have volunteers who's doing the work, most of the work as such, and we have the same problem as a number of the other volunteer teams, that things take much longer than you had hoped in the beginning. We have the three key persons here in an old shot. My moustache was slightly longer. The mission is low cost, off the shelf. We are down to 3.5 kilo. We still have 2 missions planned, but whether we will actually manage that is a good question at this moment in time. We are going trajectory like Smart 1, so it's iron engine and very, very slow. We have very low thrust, and we have had an issue, which is that we need around 50 watts to run the iron engine. And if we only have solar panels on the outside of the CubeSat, we basically have to charge our batteries for 10 hours and then run our iron engine for a few minutes, and then we can charge again for a long time before we can run again. It was not really a viable solution on getting there in time. So we could run out in elliptical spiral, which is slower, but requires less energy, but then we have a trajectory insertion problem at the moment. Now, we haven't, the situation, our mission is, we have not concluded a launch contract. Maybe this is a good time to say to John that if his DHL system really is up to delivering us to low Earth orbit at $16,000 US per kilogram, which was the figure you had yesterday. It was per pound. Now was it US pound, English pound? But that we can negotiate that, you know. But if you really can do that, we would be interested in a 4 kilo ride. And then, unfortunately, you might tell me that this is only for big packages, not for small packages. But we might have that discussion over dinner. The key issue for traveling with ion propulsion is really that you have a continuous power requirement, otherwise you can't run it. And I'll come back to that in a second, but I'll just have one on financing. We have financing for the team to go on. We are lacking for financing for the engineering development costs, which we're seeing right now, and we do not have yet the full funding for the launch cost. Now it helps if the launch cost comes down, you know, it becomes easier, we'll see. Now, we are looking for shared ride to LAO, and we are looking for partners for the Power Cube, which I will show you in a minute. We are not very picky about orbital parameters, except that we would like to go above 400 kilometers in order not to fall down before we get our iron engine started, those kind of things. I have an aside. You will remember from the last Team Summit that we had discussions with Shell. They were there at the last Team Summit and said some nice words to us. We have followed up as much as we could. I sent at least one email to most of you on that afterwards, but I just wanted to touch it here. We tried for 3 months with regular phone calls and pushing the right buttons and talking and so on, and it didn't help that our contact person left Shell just after last meeting. I think the conclusion is obvious. The oil industry is not really the place where there's money right now, but I just wanted to show you this slide, so we did close that parenthesis from last team summit. Now, key issue for us as an iron engine was really that we have a power requirement of continuous power, bigger than we can generate with the surface of the CubeSats we have. And because the surface is simply not big enough to deliver what we want. So we've been speculating on that problem, and I have a little animation of what we think is a solution to that problem, which is that you will know that there are CubeSats which have panels on the sides. They're flat, they unfold, but they still have a series of disadvantages. Not least that the sun should be so nice as to be in the right direction for them to produce power. So here is a little animation, and I will run it for you. We have put them all on top, and this is what happens. Okay, now this one has the characteristics that you can see. This is a standard cell, and there are hinges on the way, and it can actually go in and be completely flat on the top of a CubeSat and unfold to something which nearly have a 3D characteristic on the power. And I can show you this, which is just a drawing of it, how it's a little bit bigger. There is how it's sitting on top of a CubeSat. And this is the power characteristics of one of them, which basically goes between 9 and 10.5 volts all the time, completely independent of direction to the sun. It will disappear, of course, when you go into Earth's shadow, clear, but for the rest of the time, what you have is a constant or near constant power source, which for us means that we can dramatically reduce our battery capacity, which saves mass. Now, it's scalable. It gives more power per unit launch mass and launch volume, because it sits on top rather than at the side. And it's much more regular than a flat solar panel. So that's, for us, let's say, part of our path away from low Earth orbit. And we have filed a patent on it. We are in the mechanical design prototype progress, and the electrical design is in progress. We have a need for testing of the unfolding, which is a critical thing, and it has to be done in some way in zero gravity to make sure that it will actually work out there. And then, of course, the shaking and the thermal tests and all that stuff is coming afterwards. So that was what we are right now. I'd like to thank you, and I would like to say one comment to Robert, that the fact that you say that soon you might be able to 3D print space qualified parts have a significant interest for us, because we are really based on small things, and the prototypes we make at this moment in time, where a significant part of them could come in under that. So that one I might come back to you, just like I might come back to you and say, please GLXP me to low Earth orbit for 16,000 US per kilo. Thank you very much.
Any questions for Paul?
When would you like to follow up on this power concept?
The power we're doing right now.
And so would it be part of the GLXP attempt, or just as
Yes, this will be part of the GLXP attempt, because we haven't got enough power on the standard 3 or 4 U, maybe 3U cube, to drive our iron engine. So that one will go on top.
How much time do you anticipate for the unfolding, and do you think that the 30 seconds that the 0G provides would be sufficient to demonstrate what you're trying to prove?
Yes, the unfolding is something like a second, because it's a question of the springs. It's spring operated, and the most critical one of that will be to make sure that it doesn't go into block on the third loop. So there may have to be some delays on that, but really it's not a. I mean, it's a fast. It's fast. Yes. Wow. It's fast. Thanks.
How do you manage the attitude control?
We are traditionally attitude controlled with magnetism. So we have coils on board. And for very small spacecrafts, that's, let's say for CubeSats, that's sort of a bit of a standard way of doing it in Earth orbit. We have a problem when we get close to the moon. Would you switch off the camera?
Shut down.